For centuries, when early astronomers looked up, they drew what they saw on a flat plane. They charted the night sky using woodcuts and copper plates, carefully plotting the stars into rigid constellations. But these beautiful 16th century maps all shared a crucial limitation. They treated the night sky like a ceiling. They mapped the horizontal and vertical coordinates of the stars, but they entirely lacked a z-axis. There was no depth. The invention of the telescope began to crack this illusion. Observers noticed faint, cloudy patches they called nebulae. Over time, it became clear that many of these glowing smudges were vast, separate galaxies containing billions of stars. Realizing the sky had physical depth introduced a massive cartographic problem. To map the true architecture of the universe, astronomers needed a cosmic tape measure, a way to determine exactly how far away objects millions of light years from Earth actually were. The solution came from the behavior of light itself. The universe is expanding, and as light travels across deep space, that expansion physically stretches the light waves along their journey. When a light wave is stretched, its wavelength becomes longer, shifting it toward the red end of the color spectrum. This phenomenon is known as redshift, and it provides a highly reliable rule for cosmological distance. The redder a distant galaxy or quasar appears to our instruments, the further away it is. Decoding redshift finally gave humanity that missing z-axis. By measuring the color shift of incoming light, we could calculate precise distances and begin building a true three-dimensional map of the cosmos. Today, modern observatories have taken up the cartographer's mantle to execute massive redshift surveys. Telescopes like this wide-angle instrument at the Apache Point Observatory spend their nights capturing light from millions of distant objects. By measuring the redshift of that incoming light, astronomers can plot the exact three-dimensional coordinates of entire galaxies and brilliant distant quasars. When you pull all those data points together into a single map, the galaxies aren't scattered randomly. They cluster and align into organized, deliberate patterns. On a macro scale, the universe looks remarkably like a massive biological neural network. Scientists call this structure the cosmic web. To understand the physical scale of this web, we have to zoom way out. Individual galaxies cluster together by the hundreds or thousands, and those clusters align to form massive galactic walls that stretch for hundreds of millions of light years. Structures of this magnitude present a mechanical problem. Normal, visible matter doesn't generate nearly enough gravity to hold these massive superstructures together. The underlying scaffolding of the universe is actually built by dark matter. Dark matter exerts an immense gravitational pull, drawing regular gas and dust into dense, glowing filaments. As matter is pulled into these threads, it leaves behind vast, spherical voids of empty space. Every visible star, galaxy, and cluster we can see is essentially a lit-up node, clinging to an invisible, universe-spanning skeleton of dark matter. Because light takes billions of years to cross these vast cosmic voids to reach our telescopes, mapping the physical depth of space means we are also looking backward in time. This is a plot charting the average distances between galaxies relative to today. Tracing this timeline backward using light from ancient supernovas, astronomers found the curve enters this blue region, indicating that the universe's expansion and the distance between galaxies has actually accelerated. At the absolute edge of our observable map, the web structure dissolves. We see the universe before stars existed, filled with pristine hydrogen and helium plasma from the Big Bang. Mapping this physical depth provides a chronological blueprint of its entire evolutionary history. Even the vast voids between the web's glowing filaments aren't completely empty. They contain the intergalactic medium, a superheated, ultra-thin plasma of ionized gas. Within galaxies, dying stars act as cosmic engines. When they explode, they violently blast newly forged heavy elements, like carbon and oxygen, out into this intergalactic plasma. This chemical seeding process circulates the heavy elements necessary to form planets and ultimately life throughout the entire cosmic web. Early astronomers drew isolated stick figures on flat parchment, but modern cartography reveals our Milky Way is an active, chemically enriched node in a living, gravity-bound network that connects the entire universe.